Welcome back to the Explainer. Okay, today we're getting right into it. We are going to demystify exactly how C++ handles math and data, and we'll do it by building some incredibly practical programs together. If you've ever wondered how the machine actually thinks about the numbers you feed it, you are in the perfect place.
Here's our roadmap for today. We'll hit the student age problem, the integer truncation gotcha, translating algebra to C++, the modulus operator, precision with floats, and wrap up with some top tips. Let's go!
Starting right off with Part 1, the student age problem. Calculating averages to learn the basics.
All right, so imagine we need to find the average age of 10 students in a class. Simple enough, right? But to code this, we need a solid workflow. One of the golden rules of programming is to think first and then write. So here's our logical map. Step 1, declare our variables. Step 2, prompt the user for their data. Step 3, tally up the total age. And Step 4, divide that total to find our average.
Okay, step 1, what kind of memory do we actually need here? Well, we're dealing with kids' ages, so whole numbers like 11, 12, or 13. That means we're going to use the int or integer data type. And look at this setup. We are declaring 10 individual variables for the students all on one single line, just separated by commas. It's a really brilliant shorthand for declaring multiple variables of the same type. We've also got our total age and average age variables declared, ready to catch the math we're about to do.
Moving to Step 2, we actually have to talk to the user. I absolutely love how C++ visualizes this. Look at the arrows here. It's quite literally a directional flow of data. Cout uses those less than signs to push a text prompt out to the screen. And sin uses the greater than signs to pull data in from the user and stream it straight into our variable. The program actually halts right there, just waiting for the user to type a number and smash enter. Moving on to Part 2, the integer truncation gotcha, or when 12.3 magically becomes 12.
So, let's say we successfully grabbed all 10 ages, we added them up, and the total sum is 123. To get the average, we divide total age by 10. Easy, but here is where the machine throws us a massive curveball. Out here in the real world on the left, 123 divided by 10 is 12.3. But in C++ integer logic on the right, total age divided by 10 is just 12. Wait, why? Well, remember, we declared average age as an int. Yeah, our program outputs exactly 12. It doesn't round down. It literally just truncates it. It takes a meat cleaver to the decimal portion and completely chops it off. C++ integer division is incredibly strict. It only produces integer results. If you actually wanted that precise 12.3, you simply cannot use an int. You need a real number data type, which we'll actually get into in just a bit.
All right, Section 3. Translating algebra to C++. Basically, learning the local dialect of math.
So how do we take the algebra formulas you learn in school and make C++ understand them? Take the classic quadratic equation. Notice that in C++, it's not actually an equation, it's an assignment statement. The right side evaluates, and then bam, it gets assigned to y. And check out that x squared term. C++ actually doesn't have a built-in power operator for this. So what do? We just multiply the variable by itself using the asterisk. So a times x times x.
Now, as your formulas get messier, there's a golden rule you have to remember. Parentheses force the order of evaluation. Sure, C++ natively reads left to right, and yeah, multiplication naturally beats addition. But honestly, don't leave complex math up to the machine's default precedence. You really must use parentheses to explicitly dictate what happens first. It keeps your code accurate and so much easier to read. And here is exactly why that matters. Look at these two lines. In code A, C++ just follows its internal rules. It multiplies 4 by 3 first to get 12, then adds 2, and boom, you get exactly 14. But what if your actual goal was to add 2 and 4 first? You have to write code B. Putting that 2 plus 4 inside parentheses forces the machine to calculate 6 first, then multiply by 3, which gives you 18. I mean, it's just a tiny shift in brackets, but it literally changes the reality of your program.
Okay, Part 4, the modulus operator. Peeling apart numbers digit by digit.
Let's say we have a totally new problem. I want you to write a program that takes a 4-digit number, like 1234, and displays every single digit separately on the screen. How on earth do you pull a number apart like that? Enter the modulus operator, represented by the %sign. Instead of giving you the result of a division, modulus only gives you the remainder. It's kind of like the leftover pizza slice of the math world. So 1, 2, 3, 4 modulus 10. The result is 4. Just like that, we've perfectly isolated the very last digit.
Now, if we combine this modulus trick with that integer meat cleaver we talked about earlier, we get a super powerful loop. Watch this. First, 123.4 modulus 10 gives us the 4, and we print it. Next, we use standard integer division to divide 123.4 by 10. Math says 123.4, but remember the truncation? It chops the 0.4, leaving us with exactly 123. Then we feed that 123 right back in, hit it with modulus 10 again, and boom, we snag the 3. By just alternating back and forth between these two operators, we can cleanly peel off every single digit backwards.
Section 5. Precision with floats. Calculating circles with decimals.
Let's tackle some geometry, calculating the diameter, circumference, and area of a circle. Unlike counting student ages, geometric calculations almost always result in decimals. So to make sure our math doesn't get violently truncated, we're going to step away from ints and declare our variables as float. Floats allow us to store real numbers with decimal points. Take a look at how smoothly this translates on the right. We're using 3.14 as a literal value for pi, and once again, using asterisks for the radius squared instead of a power operator. And because we're using floats this time, an area of 78.5 is actually going to display exactly as 78.5, no meat cleaver. And finally, Section 6, Top Tips for Programmers. Best practices for clean code. Before we wrap up this explainer, let's lock in some fundamental best practices from our source material that really separate the pros from the beginners. First off, use descriptive variable names. Seriously, call it average age, not just X. Make sure you indent your code so it's visually logical. Always use parentheses so your math is unmistakable to both the machine and anyone else reading your code. Try to reuse your variables when you can, like we did when peeling those digits, to save memory space. Always watch out for accidental division by 0. And above all else, think first. Analyze your problem, map out the logic, and then write your code. So there you have it. You've completely tackled data streams, operators, integer truncation, and floating point precision. You know exactly how the machine thinks about math now. So the question is, what's the very first real-world logic puzzle you are going to build a solution for? Keep thinking, keep coding, and I'll see you in the next explainer.